A graduate of Swarthmore College, Chiba studied as a Marshall Scholar at the University of Cambridge and received his PhD from Cornell University in 1991. He served on the White House staff from 1993 to 95, entering as a White House Fellow on the National Security Council staff, and then serving in the National Security Division of the Office of Science and Technology Policy. After leaving the White House, he drafted the President's Decision Directive on responding to emerging infectious diseases and authored a report in 1998 on preparing for biological terrorism. He received the Presidential Early Career Award for demonstrating exceptional and potential for leadership at the frontiers of science and technology during the 21st century. Dr. Chiba currently serves on the National Academy of Sciences Committee for International Security and Arms Control, on the Monetary Nonproliferation Strategy Group, on the National Research Council National Academies Committee on the Advances in Technology and the Prevention of their Application to Next-Generation Biowarfare Threats, and chairs the NRC Committee on Preventing the Forward Contamination of Mars. Before coming to Princeton, Chiba co-directed Stanford University's Center for International Security and Cooperation for 5 years, where he was also Associate Professor of Geological and Environmental Sciences. On October 2001, he was named a MacArthur Fellow for his work in both astrobiology and international security. Professor Chiba, welcome.
Thank you all. Thank you for that very generous introduction, and I'd like to thank also the Princeton Adult School, and I would especially like to thank all of you for coming this evening. I was thinking as I was watching everyone enter the room, that I wish my undergraduate students were as timely in arriving to the auditorium as all of you were. Typically, I see them coming in about 5 minutes after the hour, so I thank you for that. What I will do this evening is give more or less the talk I would have given had I had visuals, and I'm sorry that that doesn't work out, but you know, they're mostly just crutches. So I will be able to talk without them, and I'll just try to be more vibrant and perhaps gesticulate a bit more. And I'm sorry for the feedback. I'll try moving a few things some more, and we'll see if we have any success. So let me begin by telling you a little bit about astrobiology. NASA has a definition of astrobiology. It's the same thing that people used to call exobiology. NASA would define astrobiology as the study of the living universe. Can everyone in the back hear me now? Is this good? Thank you very much. The study of the living universe. Now, astrobiology has a kind of strange history. The biologist George Gaylord Simpson in 1964 complained about what he called exobiology, and famously said in a paper in Science magazine, and this is a quote, "There is even increasing recognition of a new science of extraterrestrial life, sometimes called exobiology, a curious development in view of the fact that this science has yet to demonstrate that its subject matter exists." And that has been the gagline about astrobiology or exobiology or cosmobiology or whatever word you wish to choose, bioastronomy, according to the International Astronomical Union. That's been the gagline now for the last 40 years. The difficulty is that phrase, although it's certainly a funny sentence, it strikes a lot of astrophysicists or physicists as very peculiar. Because so much of the work that goes on in physics or in astrophysics, I'm in the astrophysics department here, so much of what goes on in astrophysics exactly concerns phenomena, the study of phenomena that may or may not actually exist. People spend decades looking for black holes before the evidence accumulated that black holes actually exist. People are looking currently for something called the Higgs boson that may or may not exist. They're looking for violations of special relativity that may or may not actually take place. In engineering, people are looking for room temperature superconductors that may or may not be possible and may or may not exist. So in fact, it's often the case in many areas of science that exactly some of the most important questions concern phenomena or objects that may well not exist. So it's peculiar that biology should somehow be in a separate category. Here, we're going to, so we're not going to worry about whether the field actually exists or not. We're just going to push on. And we're also going to know that modern ideas of astrobiology, the study of the living universe, are as concerned with the with questions of the origin of life and the planetary context for the origin of life as they are with the search for life elsewhere. And they are concerned with the interplay between the origin and evolution of life on Earth and what we are learning from solar system exploration, and vice versa. Our exploration of the solar system is informed by our knowledge of life on Earth, and I'll talk about that a bit more throughout this, this talk this evening. Let me, though, spend a little bit of time with one more definition, and that is what it is we're talking about, the idea of life. Since that is exactly what astrobiology is concerned with, we should spend a moment thinking about what that word means. And there, too, we face some dilemmas. There have been a whole series of definitions of life proposed over the years. 30 years ago, Carl Sagan, in a paper, cataloged all the different proposed definitions that have been presented and shot holes in every one of them. There have been genetic definitions, there have been thermodynamic definitions, there have been a whole range of definitions. Thermodynamic definitions, for example, talk about life as creating order in some localized region. To a physicist, one would say that life is fighting a battle with the second law of thermodynamics, with the increase of entropy in the universe. The problem with that is that there are plenty of things that most of us wouldn't call living that also create local order. Crystals, for example, are an example of a non-living substance by most people's standards, minerals that create order, they create a crystalline structure. There are metabolic definitions of life, that life takes in energy and converts it to some other form, excretes waste products, and uses some of the energy for some sort of useful work. But by that definition, arguably your automobile is alive. It takes in gasoline, and it excretes carbon dioxide and water, and it performs work. So it's in fact very hard to give a definition of life that excludes all the things that most of us want to exclude, but includes everything that is alive. If you think of life as something that necessarily can reproduce itself, then you have problems with, for example, sterile animals. So it's proven very difficult to define life, and in a paper just a couple years ago, the philosopher Carol Cleland and Dr. Cleland's at the University of Colorado and I argued that this isn't just an accident, that there are good reasons why it's been so difficult to give an account of what life is. And I'm now going to compress an entire paper down to one brief paragraph. But in essence, we analogize the situation with respect to life today to the situation that, say, Leonardo da Vinci faced centuries before there was a theory of atoms and molecules, when he tried in one of his manuscripts called the Urundal Codex to understand what water is. And you see him sort of groping with the idea of water, and he talks, that is, if you read it in translation, which is the only way I can read it, he talks about, well, gosh, sometimes it's transparent, and sometimes it's green, and sometimes it's sort of yellowish, and sometimes it tastes bitter, and sometimes it doesn't taste bitter, sometimes it's muddy. Water can be all these different things, so it's very hard to get at the essence of just what water is. But of course, in retrospect, it's not surprising that Leonardo had such a difficult time explaining what water is. Now that we have a theory of atoms and molecules, we can give an exact account of what water is. Water is H2O. You combine two hydrogens and an oxygen, and you have a water molecule. And that tells you exactly what it is. It's not so much of a definition as an identification that's situated in a theory of atoms and molecules and atomic bonds. Once you have that theory, then you can give a precise definition of what you're talking about, and it'll include cases, for example, where the water is frozen, which Leonardo's definition, or Leonardo's groping would have excluded, or for that matter, when you're talking about a vapor. We are not, obviously, in that position currently with respect to life. There is no general theory of life, or in that sense, even what we mean by biology, that we can appeal to. And in fact, it's hard to see how we're going to have such a theory until we have other examples, either other examples that we discover through exploration, or in effect, other types of life that we make in the laboratory. which arguably some groups in the country are getting close to today. So we're not going to have a definition of life. I can't give you a definition of life that I think holds water. What we're going to do instead then is that we're going to retreat from having a general definition. And for the most part, we're going to talk about life as we know it. Life is based on liquid water and on the atom carbon, as well as a suite of other elements that are sometimes called the biogenic elements, like nitrogen, oxygen, hydrogen, and so on. And of course, life is going to require energy because it is certainly going to have to maintain order. That's not unique to life that it takes an energy and creates order, but that's certainly a condition. And when we look out, especially in solar system exploration, we're primarily going to be going to sites and looking at sites with that idea of life in mind, life based on liquid water and carbon. That's not to say that there might not be other possibilities, and I'll talk briefly about those possibilities in a moment. But it's very hard to know how to go about searching for life that's not based on what we know. That's a limitation, but it's hard to know how to do much better. But again, I'll return to that. Let me, before I delve further into searching for life in the solar system or elsewhere, back further up and talk about how it is that this study is even possible. Because that is a kind of, how is it that we can even be talking about the possibility of extraterrestrial life? That depends on the kind of sweep of intellectual history that covers the last 2,500 years. If it had turned out, which it did not, but if it had turned out that Aristotle's ideas of the structure of the universe and of the physics of the universe had been correct, this conversation would be pointless. Remember that Aristotle believed that there was a kind of radical dichotomy between the heavens and the earth. There were laws of physics that applied here on the earth. In particular, objects, there were four elements, earth, water, air, and fire, and those elements moved in straight lines unless a force acted on them, and they moved towards their natural or their proper place. Their natural motion was toward their proper place. So something like this eraser, which is made mostly of earth, wants to move towards its proper place, which is at the center of the universe, not coincidentally the center of the earth, because the earth is made of earth, and it's trying to get to the center of the universe, and moves in straight lines, as opposed to fire, which, say, moves in a straight line away from the center of the universe. On the other hand, in the heavens, that's not the case at all. In the heavens, things move in circles. They rise in the east and they set in the west. And since things are moving in circles, their movement has a kind of eternal quality to it that straight line motion down here in the earthly realm clearly doesn't have. So objects in the heavens obey a different law than objects here on earth, circular motion instead of rectilinear motion. And they therefore must be made, Aristotle argued, they must be made of different stuff. Whatever sort of, they're not made of the four elements on earth, which move in straight lines towards or away from the center of the universe. They're made of some fifth element, if you will, the quintessence, and objects in the quintessential realm move in circles. So they're fundamentally different, they obey fundamentally different laws. Had that view of the universe turned out to be correct, the whole discussion of extraterrestrial life would be incoherent. It wasn't until the Copernican revolution and ultimately Isaac Newton in the 17th century where it was demonstrated that the same law of gravity that explains the acceleration of this eraser when I drop it, this speeds up as it falls towards the center of the earth. That same law of gravity explains the parabolic motion of the eraser if I throw it, and it also explains the motion of the moon around the earth in its orbit. One law of gravity explains motion here on earth, but it also importantly explains the motion in the heavens. So Newton, along with his contemporaries, but Newton did the most comprehensive job, Newton shattered this Aristotelian dichotomy between the cosmos and the earth and made it possible to talk coherently about other worlds being like the earth, or for that matter, the possibility at least of other life. So when Aristotle in his book on the heavens asks the question, could there be another earth, he talks about it for a while, but the answer is pretty clear. The answer has to be no. The idea is incoherent. But Newton returns to that question in his book, De Principio. Doesn't claim he knows the answer, but at least it's a live possibility that there could be other worlds like Earth. And therefore, there could be other life, although there's no guarantee of that. The man who kicked off this revolution, Copernicus, for whom the revolution is named, a Copernican revolution, has also given his name to something that astronomers tend to call the Copernican principle, this idea that there's nothing special about the Earth, and that by extension there's sort of nothing special about us in general. Whereas in the Aristotelian worldview, the Earth is at the center of the universe. Now it seems the Earth is just another planet going around another star in a galaxy of hundreds of billions of stars in a visible universe of hundreds of billions of galaxies. There's nothing special about us. And people have used this idea of the Copernican principle to argue, if you will, by induction of what we've learned about the place of the Earth in the universe, that there must be nothing special about life. There must be life elsewhere as well. I want to argue to you today that, in fact, we shouldn't feel secure in that argument. There may well be life elsewhere. In fact, I devote a substantial fraction of my time to questions of the search for life elsewhere. But I don't think that the Copernican principle, to the extent that it provides a guide, even necessarily requires you to take that point of view. Consider this possibility. There are hundreds of billions of stars in our galaxy. Suppose that every one of those stars has an Earth-like planet around it. We don't know that. The number's probably smaller. I'll talk about those numbers in a moment. But just imagine that there are 100 billion Earths at the right distances from their star for life in the galaxy. The dilemma is that we don't know what the probability of the origin of life is. Maybe it's very likely. Maybe once you have the right kind of planet with liquid water at the right distance from your star, you get life. The origin of life takes place. We don't understand the origin of life very well, so we don't actually know that. Maybe it turns out that the origin of life is a hideously improbable event. That there are various steps that have to occur, which can occur, but which are extremely unlikely to occur. Say, for example, that the probability of the origin of life is only 1 in 100 billion. Then you could have all these identical Earths. There'd be nothing special about our planet in that sense. But the origin of life is only going to happen on one or a few of them, because the probability of it happening on any one of them is very small. So the Copernican principle in that sense isn't violated. All these worlds are the same in terms of their conditions. It's just that it's phenomenally unlikely for life to occur. It's sort of, in this story, this is just a story, it would be like rolling 6 dice and asking how often you get a 6 on one of the dice. Well, any one of those dice could give you a 6, but probably only one, maybe none, maybe 2, but probably only about 1 is actually going to come up with a 6. And that's not because that die is special, it's just because it's unlikely that you'll get a 6. So I don't think there's an a priori answer about the likelihood of life elsewhere. If we were the only planet with life in the galaxy, the only planet where people could be having this conversation about whether there's life elsewhere in the galaxy would be this one. So there's an enormous observation bias or selection bias in our attempt to discuss that problem. So we don't know a priori, I think, about whether there's life elsewhere. And that means that it's an empirical problem, and we need to go look for it if we're interested in the question. And my view is that it's one of the great questions, one of the great intellectual questions for the human race. So I think it's worth looking for it. And today I'll talk about 3 ways that we're currently going about looking for life. One is in situ searches in the solar system, so go there and have a look with spacecraft primarily, maybe in the future with human beings. And so you can either send your spacecraft there and conduct experiments on the surfaces of these other worlds, or, and a little bit more ambitiously than we've done yet, except for the moon, you can scoop up material and bring it back to Earth and examine it more carefully here on Earth. The second way to look for life is to look for other worlds, presumably worlds like the Earth, and to try to analyze the composition of their atmospheres. We can't quite do that, but we're going to be able to do that soon, and I'll return to that later in the talk after I move out through the solar system. And then the third way we currently have to look for life is to look for manifestations of technology. And the most systematic way of doing that is through the so-called search for extraterrestrial intelligence, searches for typically radio waves transmitted by other civilizations. Each of these kinds of searches makes certain assumptions. Let me begin with the search for life in the solar system. And in particular, I want to emphasize that the knowledge we have of life on Earth informs the way we go about searching for life. One example. We've learned over the past 10, 15 years that there is a so-called deep biosphere on the Earth. The total mass of everything living on the Earth, at the surface of the Earth, turns out to be about 10 to the 18 grams, a billion grams of material. most of that in the forests, by the way, at the very surface of the Earth. There's also a deep biosphere, almost entirely single-celled organisms, bacteria and something called archaea, microbes, that live underground, down miles underground, kilometers underground. And there have been some efforts made to estimate what the biomass of that subsurface biosphere is through deep drilling and being very careful not to be introducing contamination. And it looks like the deep biosphere, which extends, as I said, kilometers under the subsurface, contains about 10 to the 18 grams of bacteria. In other words, there's as much stuff in single-celled organisms living beneath the surface of the Earth as there is on the surface, including all the trees, which is a startlingly different way of thinking about the biosphere of the planet Earth. And it informs the way you think about how you might go searching for life elsewhere, and makes certain environments elsewhere in the solar system credible in a way that they might not otherwise have been. In particular, there may be, it appears that it's the case, that there are fractions, probably small parts of the deep biosphere, which are entirely independent of surface conditions on the Earth. That is to say, if the sun were to go out tomorrow and the surface of the Earth were to freeze over, there would still be some ecosystems in the subsurface that would survive. They would survive down to the depth where the internal heating of the Earth, the radioactive and other heat sources in the interior of the Earth, would maintain a layer in the subsurface where liquid water could continue to exist. And in that area, in that region, there would be bacteria and archaea, single-celled organisms, that could make their living, for example, by combining carbon dioxide dissolved in water with hydrogen weathered from rocks. And as far as we can tell, ecosystems like that exist today don't depend at all on what the sun is or isn't doing. A lot of the organisms that live in the subsurface indirectly, often in some subtle way, do depend on the existence of photosynthesis at the surface of the Earth, but it appears that some subsurface life does not. And that makes subsurface environments elsewhere in the solar system, such as the subsurface of Mars, or the subsurface of Jupiter's moon Europa, where there appears to be another solar system ocean, much more plausible as venues for life, as places that we want to search. And our understanding about life runs in the other direction as well. You can't talk reasonably about the origin of life on Earth anymore without taking into account what we've learned from exploring the moon. One of the most important scientific discoveries with the exploration of the moon was that the early inner solar system, the moon and the Earth in particular, but also Mars and Mercury and presumably Venus, were subjected to a much greater bombardment of comets and asteroids in the first 700 million years of solar system history than is the case today. Much greater. And so when you look at the surface of the moon, right, all the dark, remember the dark splotches you see on the moon, those dark circles, those are dark circles because those are giant craters that were excavated on the moon that were filled in by dark basaltic lava. The crater is big enough for you to see when you look at it. The moon is saturation crater. Every part of the moon has been cratered, so that now when you add more craters to it, you're just putting one crater on top of another previously existing crater. The Earth experienced all of that. In fact, it experienced probably about 25 times more cratering than the moon did. But we've erased it because we're very active geologically. We have erosion due to rainfall and so on. By going to the moon, we learned what conditions on the Earth were like. And in particular, from the timing, from our ability to radioactively date rocks from the moon, we discovered that about 4 billion years ago, this bombardment was especially intense. So at exactly the time on Earth that life was trying to originate, it appears that Earth was subject to this incredibly intense bombardment of comets and asteroids, which is a challenge for the origin of life, especially since the several biggest of those impacts may have evaporated the Earth's entire oceans repeatedly, which is bad. So what we've learned through solar system exploration informs our understanding of the origin and evolution of life on Earth. In the same way, with some danger attached, that what we think we know about life on Earth informs the way we search for life elsewhere in the solar system. Now, having said that, the Earth is still unique in the sense, in our solar system, in the sense that it has abundant liquid water at the surface. At the surface of the Earth, water can be present in 3 phases: liquid water, solid ice, vapor. And that's not really quite the case for any other world in the solar system, although Mars is looking more intriguing with respect to liquid water all the time. So I'm going to briefly walk through the solar system and talk about the most likely venues for life based on prospects for liquid water, and also, less important as a selection criterion, prospects for elements like carbon to be present. And I say less important because carbon pretty much turns out to be everywhere. Liquid water really is the key limiting factor at this point in our understanding for life as we know it elsewhere in the solar system. Just because liquid water might be someplace doesn't mean there's going to be life there, but it's a prerequisite to the extent we understand life. I'll segue briefly now, and we can leave a further discussion of this to questions if anyone's interested. I'll segue briefly just to life as we don't know it. Those conversations about life as we don't know it usually fall into two categories. One is a suggestion that you substitute some other liquid for water, liquid water. And the other is a suggestion that you substitute some other fundamental atom for making your molecules of life for carbon. Why do you need liquid at all? Well, you need some medium for the reactions, for the chemical reactions of life to take place in, unless you're imagining such a radically different form of life that while we can talk about it in a science fiction way, we're not going to be doing any kind of useful experiment searching for it anytime soon. So one is free to imagine other liquids, liquid ammonia, for example, instead of water. Life based on liquid ammonia would be life based on a solvent, the liquid in which chemistry occurs, that has a lot of properties similar to liquid water, but it would be much, much colder. So everything would happen more slowly. That perhaps would make the life more vulnerable to the external environment, but it's probably not a showstopper. You just need to find some place that seems to have abundant liquid ammonia, and you probably want to search that place. Alternatively, you could imagine a liquid solvent for life that's radically different than water, such as a hydrocarbon, like liquid methane, natural gas. That's radically different because water is in effect a charged molecule. It has a kind of positive end and a negative end. And that makes it possible for water to dissolve things like salts easily. It affects the shapes of molecules, the molecules of life. Whereas a molecule like methane, natural gas, doesn't have those charged ends at all. So its chemistry, the chemistry of life based on something like methane, would have to be radically different from the chemistry of life based on water. So it's very hard to go very far with speculations about what that life might look like. But one might hope that one could explore an environment where there was abundant liquid methane instead of liquid water, and maybe get some sense of whether life might be possible under such conditions. The working fluid on Saturn's moon Titan is liquid methane. On the moon Titan, there appears to be a kind of meteorological cycle that involves methane. Methane evaporating into the atmosphere, raining out, also ethane rains out, collecting on the surface. So there does seem to be one world where the relevant fluid isn't liquid water, but is liquid methane. And from that point of view, Titan is a very interesting place to explore when doing a kind of initial, barely scratching the surface investigation of a possible, very different type of life. With respect to changing the basis of life, we talk about carbon-based life. The usual science fiction suggestion is that instead of carbon, maybe you could base life on silicon. And the reason people talk about silicon is because if you were to see a periodic table of the elements, you would see that silicon sits right underneath of carbon in the periodic table, which is another way of saying that the chemistry of silicon is very similar to the chemistry of carbon. In fact, the chemistry of silicon is less diverse than the chemistry of carbon. It doesn't make the kind of double bonds that carbon atoms do. So even silicon is more limited than carbon. But empirically, it seems to be worse than that. When we look out into the galaxy, we can use radio telescopes to determine the kind of molecules that are in the so-called interstellar medium. The space between the stars has, at a very low density, molecules floating in it. And we've cataloged something like 100 molecules in the ISM, the interstellar medium, that are based on carbon. There seems to be a rich carbon chemistry, which is to say an organic chemistry. All organic means is based on carbon. A rich organic chemistry everywhere in the galaxy, in the spaces between the stars. We also know there's organic chemistry throughout the outer solar system. Again, no indication of biology, just carbon-based chemistry. When you look in the interstellar medium, you do not see an analogous chemistry based on silicon. There just isn't some analogous rich chemistry based on silicon. So by probing the interstellar medium, not because we were testing some hypothesis about life based on silicon, just because we wanted to find out what molecules were out there. We seem to have gotten some information about the prospects for life based on silicon rather than carbon. And so far, I would say it doesn't look good. Presumably, you need a kind of rich chemistry, and silicon doesn't seem to be providing us that chemistry elsewhere in the galaxy, to the extent we've been able to look so far. So let me say a few more. I'm from the rest of this talk, I'm retreating until the very end. I'm retreating from life as we don't know it to life as we know it, and I'm going to talk about searches for life in the solar system now that amount to searches for life as we know it, and really amount to searching places where we think liquid water might exist. The moon, by the way, is bone dry. Dry, dry, dry. There may be some ice, there may be some water ice in craters near the poles. That's very important, even in the subsurface. That's very important to find out from the point of view of future human habitation. But prospects for life on the moon seem at this point extremely dim. Let's move farther out away from the sun, though, and go to Mars. And there's been, as you know, this incredible exploration of Mars over the past decade, and it's not going to stop. Between the US, Europe, Japan, we're going to be launching to Mars at least every 2 years. There are 5 spacecraft at Mars now. That sort of pace is going to continue. Yes, the NASA budget is under great pressure, and we can talk about that, but basically, this kind of aggressive exploration of Mars is going to continue, and our knowledge of it is exploding in leaps and bounds. One of the things that does seem to be becoming clear from the last decade of exploration is that there's a lot of water on Mars. Most of that water seems to be frozen. We have some dramatic images of glaciers on Mars, of craters that have circular ice deposits in their bottoms, of ice layering near the poles of Mars. So there's plenty of ice. And in fact, using instruments on the spacecraft, we've been able to probe the Martian subsurface, not very far down, to about 1 meter or so. And we discovered that when you start getting near the poles, 70–80% of the upper meter of Mars is water. So there's a lot of water in frozen form on Mars. The question from the point of view of life is how much, if any, of that water is liquid. Well, the more we learn, the more it appears both that there was once a lot of liquid water on Mars. One of the Mars exploration rovers has suggested that in images of what appear to be sedimentary rocks that were laid down in liquid water. But also that the possibility for liquid water on Mars today seems to be quite credible. Really for 2 different reasons. One is observations of gullies on Mars that sure look as though they've been carved by flowing liquid water in the geologically recent past. And when I say the geologically recent past, I mean the last few million years. You can't date things on Mars better to an accuracy of more than a few million years. So that could mean yesterday. It could mean a few million years ago. The point is very recently. And in fact, there is now one such gully that has shown up in an image that was taken recently and wasn't in that image about 3 years ago. Now, that's not proof that that gully was cut by liquid water, but at least some of these gullies sure do look just like gullies on Earth that are cut by liquid water, include down to the kind of fan of debris at the bottom that seems to have been deposited by running water at the base of the gully as they run down the slope. So there's a geomorphological indication that water at least occasionally flows on the surface of Mars today. And in fact, there's kind of a chemical argument that this shouldn't surprise us, or at least intermittent liquid water near the surface shouldn't surprise us. The average temperature on Mars is something like 210 degrees Kelvin, minus 60 centigrade. Okay, that's cold. But it is cold. But Mars has an extremely salty surface, and if you make your water very salty, you can keep water, liquid, down to at least tens of degrees below the normal freezing point of water. And the result of that, when you sort of plug it into temperature variations on Mars by latitude and the change in temperature as Mars rotates, so that as it goes from night into day, it looks as though right now there is really no region on Mars where you can exclude with confidence the possibility that there isn't liquid water intermittently in the near surface, underneath the Martian surface. That doesn't mean it's there, but it looks currently like it's possible. And that has important implications for what's called the for preventing what's called the forward contamination of Mars. And in fact, in just the last 2 years, and we're wrapping this up now, I chaired a committee for the National Academy of Sciences on preventing the forward contamination of Mars. The committee was requested by NASA, which rightly recognized that given what we've learned about Mars and given what we've learned about single-cell organisms on Earth that can survive extreme conditions, that say, like very cold temperatures, they can survive freeze-thaw cycles, they can survive high salt concentrations, they can survive high radiation. Given increasing knowledge about those microorganisms, plus knowledge of Mars, that we need to be particularly concerned about whether we can carry microorganisms to Mars on our spacecraft that could then survive once they get there. This concern goes by the name of planetary protection. It dates back to the late 50s with some agenda-setting letters and then papers by the Nobelist Joshua Lederberg, Nobel biologist Josh Lederberg. But it was really given legal instantiation in the 1967 Outer Space Treaty, which requires spacefaring nations to avoid the harmful contamination, that's the phrase that's used, the harmful contamination of other celestial bodies. And the way that phrase has been interpreted is that if countries are going to go to a world, for example, to search for life on that world, then bringing bacteria with you that could survive on that world, which would then interfere with your attempts to search for life, because maybe you detect the life that you brought with you, or worse yet, the life that somebody else had brought with them on their spacecraft, that would be harmful contamination, and you should really take steps not to do that. It's interesting from this point of view that the legal interpretation that's been applied by NASA, that's been applied by the international body that tracks this sort of thing, has been that the reason you have to avoid contaminating other worlds is so that you don't muck up scientific experiments. It's not, and it has never been, that there is some ethical obligation to protect the potential biosphere of another world. But there is currently a requirement that you not run the risk of mucking up science. So we were asked to look at what NASA currently does with respect to preventing forward contamination and make suggestions for, first determine whether it's sufficient, and if not, make suggestions on how to do it better. This could be, and indeed has been on occasion, an entire lecture in itself, and I'm not going to give you that lecture. But let me say a couple things. The problem is credible. The problem is credible for a number of reasons, but most dramatically because we know that certain types of bacteria can survive years in space. We flew an experiment in the 80s called the Long Duration Exposure Facility. It was only supposed to be up for a short period of time, but because of the Challenger catastrophe, it was up for 6 years. And among many other experiments on the LDEF, there was an experiment testing the survival of certain types of bacteria in space. And there have since been some European experiments as well. And what we know is that as long as these bacteria, the ones that were flown, we only have data for about 3 species of bacteria, by the way. But for the ones that were flown, about 25% of them survive a year in space, as long as they're protected against ultraviolet light from the sun. So if you're on an interior surface of your spacecraft, 25% of you survive a year. You freeze dry, you're in vacuum after all, you freeze dry, but that's fine. When you're introduced to liquid water later, you rehydrate and you go on living, reproducing, and so on. If you're in space for on the order of 10 years, well, the experiment was run for 6 years. If you're in space for 6 years, about 1% of the organisms survive. The dilemma from the planetary protection point of view is it only takes about 8 months to get to Mars. So there is no question that when our spacecraft arrive at Mars, there are viable bacteria on at least the interior surfaces of those spacecraft. Now, spacecraft are assembled in clean rooms, so typically so-called Class 100,000 clean rooms. But a Class 100,000 clean room has thousands of spores on the surface per square meter. A spore is a particularly hardy form of microbe. And we don't actually know how many other types of microbes are on surfaces in clean rooms because we actually haven't collected data for that. We don't really know who we fly in our spacecraft. By who, I mean what kind of organisms we fly in our spacecraft. We don't have comprehensive data using modern DNA methods for the organisms in our spacecraft. The more we learn, and we can't culture most organisms on Earth. We can probably only culture about 0.1% of the microbes in the terrestrial environment. We only know they're there from their DNA. So we don't know who we're flying to Mars. And it looks like at least some terrestrial bacteria, bacteria that like low temperatures and high salt contents, psychrophilic halophiles, for example, might be able to survive certain Martian environments. So the conclusion of our study, which is probably, I've chaired a lot of committees, and this is probably the single most contentious committee I've ever chaired, but we have a unanimous report. It's been published in pre-publication. You get it on the web, the National Academy website. It's about to come out in hard copy. Basically, the conclusion of our study is that we need to do this right, which means we need to use modern DNA methods to assess who's on our spacecraft, try to make some evaluation of whether they could survive on Mars, and use more recent methods for reducing the load of organisms on our spacecraft. Doing this right probably requires a research program that will take until launches in 2016 to implement. Our committee included biologists, planetary scientists, spacecraft engineers, experts in sterilization, and the spacecraft engineers were critical to us walking through this timeline. We're not going to start doing things right till about 2016. So the question is, what do we do in the interim? And the report makes some suggestions on, given our current knowledge and what we can do, on what we should do. And basically, we argue that we need to tighten up our current procedures, which frankly, if implemented, remember, we're just making recommendations, if implemented, will make missions a bit more expensive, because you're going to have to be more careful about trying to sterilize your spacecraft. And it's those latter recommendations that are the most controversial in the report, because they impact what people are trying to do with spacecraft more or less right now, as opposed to what happens 10 years from now after a lot of research, and you can sort of imagine pushing that off till I get out this door. But in the meantime, we're saying there are certain things we have to do more or less right now. The other thing our report says, there are 17 recommendations in the report. One of those recommendations says, you know, it's not our mandate. We have a statement of task we have to operate in. We're held to that. Our statement of task doesn't allow us to reconsider the purpose of planetary protection, whether it's about protecting the science, as people say, or protecting the planet, in this case the planet Mars, whether we have some responsibility to a potential Martian biosphere not to contaminate it. Evaluating that question is beyond our statement of task. Moreover, we didn't have the kind of expertise on the committee, such as planetary ethicists, that one would really want to have to evaluate that question properly. So we can't, but you know what? People really ought to think about this harder, and NASA and the relevant international committee, which is called COSPAR, should hold an international conference to ask whether we need to think about reinterpreting the requirements of planetary protection to include protecting the planet as well as protecting the science. So that's Mars. We don't know if there's life on Mars yet, but it's looking more intriguing. And there's an aggressive program of exploration that I think is going to tell us a lot more over the coming decade. I'm going to speak, since we got a slightly late start, I'm going to speak for another 5 or 10 minutes, and then I'll just take questions for however long everybody wants to keep asking questions. Let me move a little farther out in the solar system, and then let's talk about other ways to look for life. The other destination in the outer solar system is Jupiter's moon, Europa, one of the 4 big moons of Jupiter, one of the moons that Galileo saw with his telescope. And Europa is especially intriguing because it appears that Europa is another world in the solar system with a liquid water ocean. And in fact, the best models, and I really want to emphasize that these models are essentially not controversial now in the solar system exploration community. The best models, there are 3 lines of evidence for a subsurface liquid water ocean on Europa, and the best models suggest that that ocean is about 100 kilometers deep. It's a world the size of the moon, and when you do the math, that gives you an ocean whose volume is about twice that of the Earth's oceans. So it really is an ocean of liquid water on Europa. These are models that rely on 3 different lines of evidence. I think the evidence is pretty strong, but I wouldn't say it's definitive. I would say that it's very likely that this ocean exists on Europa. In the late 90s, I chaired a committee that was asked to set the science goals for an orbiter mission to Europa. And the first goal we set for that mission was to absolutely nail this question of whether the ocean's there. And then if you're really sure the ocean's there, then you want to start exploring places on the surface where it looks like the ocean has bubbled up through the ice shell. The ocean is under about 10 kilometers, about 6 miles of ice, with uncertainties in all those numbers. So the ocean's protected by this layer of ice, but there are places on the surface where it looks like the ocean, one way or another, material from the ocean has reached the surface, and it sure would be nice to access some of those areas and see what's frozen in that ice. That mission, by the way, got canceled, never flew. It was revived early in the first Bush administration as part of their push for space nuclear power. So it rapidly escalated to the billion-dollar level because it was going to involve developing a whole new energy source and flying reactors in space. That's now been canceled. And NASA's returning to something that looks remarkably like what we were talking about a decade ago, although that's now also getting pushed off the table as science is slowly squeezed out of the NASA budget. So it's not clear we're going to get back to Europa anytime soon. It's going to be, if all the stars align to get back to Europa a decade from now, I think it's more likely we'll get back there 20 years from now, which is a shame because if I were placing bets for life elsewhere in the solar system, my first bet would be on Europa, just because there appears to be so much water there. And it's not that far from the surface, and it appears we can probably access it indirectly at the surface without having to actually dig down through all that ice. So let me leave the solar system. I just talked about Mars and Europa, and I said just a little bit about Saturn's moon Titan. And let me end by talking about two other ways of looking for life. One of those ways is a way that we can't quite yet do, but we're on the verge of it, and that is to look for signs of life in the atmospheres of other planets orbiting other stars. Remember, we have detected giant planets around other stars. We've detected, must be about 150 giant planets now orbiting other stars. We've begun to determine the atmospheres, the atmospheric composition of a few of those giant planets. What we haven't been able to do yet, with only a few exceptions, is to detect worlds the size of Earth around other stars. So at this point, one would have to say, honestly, we don't know if there are other Earths, worlds the size of Earth, made mostly of rock, that are at more or less Earth's distance from their parent star, or more precisely at a distance from their parent star, where liquid water oceans could exist right at the surface. We don't know the answer to that question, but we're about to know the answer to that question. There's a mission called Kepler, which, God willing, is going to fly later this decade. It's in process now. And Kepler is going to determine the presence or the absence of Earths around a sample of 100,000 stars. It's basically going to sit and look at 100,000 stars long enough to determine whether there are worlds the size of Earth orbiting those stars. And it will give us statistics. So after Kepler, we're going to know what fraction, and this is a mission failure, we're going to know what fraction of stars have worlds, have planets the size of Earth, and we're also going to know what distance those planets are from their stars. So we're going to know what fraction of those are at the right distance from their stars for liquid water to exist on their surface. Now that doesn't tell us whether there's life on those worlds or not, but as I said earlier, people have been speculating about whether other Earths could exist for at least 2,500 years, since Aristotle, and it's incredible to me that we're actually going to know the answer to that question probably in the next few years. Not only whether other Earths exist, but what their statistical frequency is. What fraction of stars have them? And are they at a distance where liquid water could exist on their surfaces? This is a kind of extraordinary transformation in human understanding of how we fit into the rest of the universe. Yet it's one that's gone almost completely unobserved, I think, in terms of the attention that's been paid to this mission. In fact, I would be willing to wager if one did a poll that more people know the details of Britain's prenup than know the details of the Kepler mission, which is largely the fault of all of us in the scientific community. Somehow we have to do a better job of breaking through. Now, Kepler's only going to tell us about whether those worlds exist. There's another generation of missions which have all been canceled in the current budget, which would then go on to analyze the atmospheres of those worlds. And the atmospheres, the composition of the atmospheres might give you clues about whether life exists on those worlds. For example, if you were looking at the Earth's atmosphere from another star, if you could do the measurements, you would recognize that the Earth's atmosphere simultaneously had all this oxygen in it, 21% or so oxygen, and it had a ridiculous amount of methane. Small by our standards, but many, many, many orders of magnitude more methane than had any business being present in an oxygen-rich atmosphere. And you might speculate that chemical disequilibrium, the presence of the methane and the oxygen simultaneously, when the two ought to just combine and make carbon dioxide, is because both are being produced by life. O2 by photosynthesis and methane from a whole variety of sources, including bacteria called methanogens that produce methane. So we might get some clues by looking at atmospheres of worlds around other stars about whether there's life on them or not. But this is going to be a difficult kind of analysis to do. And an example of why it's going to be difficult, we've just seen at Mars. There's methane in the Martian atmosphere. Mars has a very oxidizing atmosphere. The methane shouldn't be there, yet it is there. Maybe that means that methane on Mars is present at about the 10 parts per billion level. It's not like there's a lot of it, but way more of it than should be there just from the chemistry. Maybe that's because it's being produced by something like methanogens in the subsurface of Mars. Maybe it's a hint that there's life on Mars. Maybe it's evidence that there's life on Mars. The problem is, almost as soon as that observation was announced, other theorists rapidly produced other papers that were published which showed various ways you could produce the methane in the Martian atmosphere without using biology. So Mars is kind of providing a test case for us of the kind of controversies we're going to see once we actually start cataloging the composition of atmospheres around, of planets around other stars. Finally, a third way to look for life would be to look for manifestations of technology. And a systematic way to do that is the so-called scientific search for extraterrestrial intelligence, which can be done in more than one way, but the way it's typically been done has been through a search for extraterrestrial radio signals. That actually makes sense from the point of view of broadcasting in the galaxy. There's noise at various wavelengths in the galaxy, and it turns out that the place where the noise is least, where the galaxy is most transparent, if you were trying to signal, is in the microwave region of the radio spectrum. So that's true for most stars in the galaxy. So pretty much, in that sense, everybody knows that if you want to broadcast a signal across great distances in the galaxy, if there is any everybody out there, that the microwave frequencies are the frequencies to use. Modern searches, which are conducted, the most sensitive searches are conducted by the SETI Institute in California, and as a lawyer would say, for interests of full disclosure, I need to say now I'm on the board of trustees of the SETI Institute. Modern searches don't assume that the other side is transmitting at any particular frequency. In fact, they scan billions of frequencies. They look for very narrow frequencies, which would be indicative of technology. There's a fundamental reason why natural processes aren't going to produce extremely narrow frequencies. And they allow the frequency to drift. They allow the frequency to drift. So they're very numerically intensive. These searches are only possible because of Moore's law in computing, where computer power doubles every 18 months or so. The SETI Institute, with private donations, is now building a new dedicated radio telescope to be called the Allen Telescope Array, funded substantially but not entirely by Paul Allen, which is going to allow us to look at the million-nearest stars over the next decade. That's still a tiny fraction of the stars in the galaxy. Remember, the galaxy contains hundreds of billions of stars. So even after that decade, we will have looked at a tiny fraction, about 1 part in 100,000 or so, of the stars in our galaxy. My own view, my personal view, is that the galaxy would have to be replete with broadcasting extraterrestrial civilizations for us to have any significant chance of being successful. I suspect that intelligent technical civilizations are quite rare, although that's a little more than a prejudice currently. There's a series of arguments that go, in some cases, go back a century to Alfred Russel Wallace in 1904 about whether intelligent life is common or rare in the galaxy. There are at least 4 such arguments that are kind of interminable. The argument's well known, the responses to it are well known, the responses to the responses are well known. And if I had more time, I could spend the next hour recapitulating all 4 of those arguments. I mean, fundamentally, none of them is decisive, and that again means that we're in the realm of having to conduct a search. And we're only going to answer this question empirically by actually going out and having a look, which in small steps is what we're trying to do. I'm very happy to take questions, and thanks for putting up with a no-image lecture. And then I'll come down. Gentlemen, yes.
I was wondering, early on you had mentioned that you thought it was somewhat of a coincidence that I don't know how many billions of years ago the Earth was being bombarded by asteroids and comets and things like that, just at the same time life was trying to occur. So what's your thought of this whole seeding theory of life?
Thanks. So for those of you who might not have heard, was it really a coincidence that the Earth was subject to this heavy bombardment of comets and asteroids just about the same time that, that life seems to have originated on Earth? There's a whole discussion here about how well we know the timing of the origin of life on Earth and how well we really know the early bombardment. My grad student Kevin Hand and I have recently surveyed that in a review article in the Annual Reviews of Astronomy and Astrophysics, among many other things. So you can find all the details there. Let me encapsulate that down in just a few sentences. So the heavy bombardment seems to have ended by about 3.8 billion years ago. By that point, or shortly thereafter, judging from the crating record on the Moon, the bombardment of comets and asteroids of the Earth-Moon system is about what it is today, comparatively much lower than it was earlier. The origin of life, evidence for the origin of life, is reasonably firm, but not certain, at 3.5 billion years ago. And there's some evidence which recently has become extremely controversial at 3.8 billion years ago. So there are two ways of looking at this. One way is that heavy bombardment made the surface of Earth unbearable, and that the origin of life didn't occur until just after maybe, it was over. And there's a set of papers that have been published on that. You can look at that somewhat quantitatively. You can ask, for example, how often did the Earth get hit by something big enough to have boiled the entire oceans, which would be bad for the origin of life. In fact, there may have been repeated impact sterilizations of the Earth in this field. The flip side, which you mentioned, is that, in fact, this bombardment may have contributed to the origin of life. And it could have, one can imagine it could have done that in several ways. And the most extreme way is that you would imagine that comets and or asteroids, or at least some of them, actually contain viable organisms that are carried between planets or between stars and delivered to various worlds. So this is sometimes called microbial transfer, interplanetary or interstellar microbial transfer, or sometimes it goes by the quaint name of panspermia. There are a lot of objections to that idea, not within the solar system. That is to say, the Earth and Mars could have probably successfully transferred microorganisms back and forth. But trying to do it across interstellar distances is extremely difficult because of the radiation background. Either because it takes so long to travel between the stars. So you just are subjected to either galactic cosmic rays over a long period of time, or if you're buried deep in an object where you're protected, you're shielded against the cosmic rays, you have the natural background radiation that's embedded in the rocks of that object. So it's just very hard to do across interstellar distances, although probably not quite impossible. The next suggestion, which isn't that radical, is that, well, gosh, we know that comets and certain asteroids are chock full of organic molecules. Comets look like they're 18% or so organic molecules, carbon molecules. Maybe some of the molecules needed for the origin of life, including potentially amino acids, were delivered to the Earth in comet impacts. I spent a lot of time with that question in my PhD thesis with Carl Sagan, recently with Elisabetta Piarazza. It's hard to do because comets hit the Earth very fast, so there's an enormous amount of energy in a cometary collision with the Earth. If Comet Halley were to hit the Earth, the ensuing explosion has an energy of 100 million megatons. Okay, a large nuclear warhead in a Soviet or in a former Soviet or U.S. arsenal is on the order of a megaton. These collisions are enormously energetic. It's hard to see organic molecules surviving them easily, and yet it turns out that in collisions of kilometer-sized objects, some organic molecules probably do survive. There have been a series of papers published on that. And under some circumstances, which aren't extreme, it turns out that the supply of certain molecules that could have been important for the origin of life, such as certain amino acids, on the early Earth might have been dominated by input from comets. Very long, detailed subject. That's all I'm going to say about it. The last thing to say is comets are also about 40% water. Some asteroids are very rich in water. So you also have to wonder whether this sort of veneer of ocean on the outside of the Earth might have been a late delivery due to comet and asteroid impacts at the time of the heavy bombardment. Models of Earth formation suggest that in the region of around the sun where the Earth formed, things should have been pretty dry. So it looks like you do need to appeal to stuff coming in from farther away to account for the oceans of the Earth. Yes, sir, and then I'll come down.
Do we know whether the microbial organisms deep down have the same origin as life on the surface?
So I think most of you probably heard that. Can we say anything about the origin of life in the subsurface versus the surface? And the short answer to that is no. We really don't understand the origin of life. There are some hints, however. But none of the hints should be taken too seriously because, once again, there's already kind of familiar argument, counter-argument. So let me just give one example of a hint. Let me say subsurface life shares a common ancestry with life at the surface. There's no question about that. You do the DNA sequencing. All life that we've sequenced DNA for on Earth slots into one evolutionary tree, the so-called phylogenetic tree. So there's a common tree of life for everything on Earth. There's a little bit of tautology in that statement because there's an important question about how we would ever detect microbial life that was radically different from the DNA-based life that we know about. You can't culture even most DNA-based life. You can culture 0.1% or 1% of it, that is, raise it up in a petri dish. We only know it's there because of its DNA, and we only detect its DNA because we use certain DNA segments called primers that identify certain regions of DNA and then allow you to make many copies of it so you can work with it. So if there were microscopic organisms, even on the Earth, that didn't have those so-called universal DNA sequences or didn't have DNA at all, it's not at all clear that we would know it's there. So there is a little bit of tautology in this statement. But the stuff we've detected in the subsurface is clearly very closely, the same, it shares the same common ancestry with life on the surface. The next question is, did life originate in the subsurface or did it originate at the surface? If it originated in the subsurface and then sort of migrated up to the surface, that makes places like Europa, say, seem much more interesting for the origin of life, because there you're shut off from the sunlight at the surface by kilometers and kilometers of ice. We don't know the answer to that question. If you work your way through this phylogenetic tree, this common tree of life on Earth, what you see is that the organisms that are closest to the root of the tree are organisms that like to live at high temperatures, so-called thermophiles or even hyperthermophiles. And there's a story you can tell that means that the origin of life took place at depth because temperatures go up as you go down the surface of the Earth because of the geothermal heating. So maybe the origin of life occurred way down there, and then eventually life migrated up to the surface. One problem with that story, even taking those data at face value, one problem with that story is what I've already described as the impact environment of early Earth. If the largest asteroid collisions with Earth actually did boil the entire oceans on several occasions, and that seems quite plausible if you work through the numbers, then you could have had an origin of life at the surface of the Earth. Life migrated down to the subsurface. We got smacked by one of these ocean boilers. The surface of the Earth was sterilized. The only organisms that made it through were the ones that had migrated down to the subsurface, which then repopulate the surface of the planet. So life goes through this kind of impact bottleneck, and you get the impression that life originated in the subsurface, but that's only because you had a surface sterilizing event. Well, that seemed to have quieted everybody.
Have you given any thought to what intelligent life would look like?
Have I given any thought to what intelligent life would look like? Yes, I have. Let me make this is a glib statement, then I'll justify it. I think other intelligent life will look like whatever it wants to look like. And now let me justify that statement in two different ways. Well, it's really kind of the same way I said twice. I mentioned already in this talk Moore's law in computing, where computational power doubles every 18 to 24 months. And you can measure that in different ways. You can measure that in terms of the number of transistors you put on a chip. You can measure it in terms of cost, how expensive chips are. But basically, computational power is exponentially increasing with the doubling time of, say, 18 months, so-called Moore's Law, Gordon Moore of Intel. You can make a comparable kind of plot that measures the power of biotechnology, a kind of fundamental measurement of biotechnological power. And I would show you that plot if I could. So for example, you can ask how long does it take to synthesize what's called an oligomer of DNA. A DNA chain of a certain length. How long does it take to synthesize that chain? And use that as a kind of proxy for what we can do with biotechnology now. And it's a serious proxy, right? Because a few years ago, a group at SUNY synthesized the poliovirus from scratch, right? They bought the chemicals off the shelf and they synthesized the poliovirus, viable infectious poliovirus in the laboratory. A few years later, another group synthesized a different virus, a much safer virus, but one of comparable length from scratch in 2 weeks. Okay, so how long it takes you to synthesize DNA of a certain length, now that all these genomes, the DNA sequences for many organisms, including very dangerous organisms, are available on the web, is an important measure of biotechnological power. And you can plot that over time. The plots don't go as far back as Moore's Law because biotechnology is younger technology, but you can plot it back to 1985 or so. And what you see when you make those plots is that biotechnological power has also been increasing exponentially. As you plot it on a log linear scale, you get a straight line. And in fact, the speed, the magnitude of the exponential is greater than the Moore's Law exponential. So we're already in an exponential phase of biotechnological power increasing. And there's no end in sight currently for that. And my own view is that, and that's also true for costs. The costs are declining exponentially. So that within a decade, we'll be able to, any one of us, if this continues, we'll be able to have our entire genome sequence for about $1,000. Which will introduce a whole new era of genomic medicine, which will be great for those of us who live in the developed world. We can take advantage of that. But along with it will become an enormous amount of power that's available to small groups that are technically competent to do all kinds of genetic manipulations. That has an obvious grim side, which isn't the subject of this talk, but it also suggests to me that there may only be a pretty brief period of time in a kind of bottleneck, if you will, in which a civilization is technological, but it also resembles whatever species it biologically evolved as. I suspect that's a pretty narrow window. In that sense, I think we're in a kind of special time right now, assuming we make it through the bottleneck. And then I think in the long term, intelligent, and probably not the very long term, intelligent civilizations will either through genetic manipulation or through machine biological interfaces or through artificial intelligence, if it turns out that artificial intelligence is actually possible. I view that as a hypothesis that's yet to be demonstrated. There's some objections to the possibility. But through one means or another, I think technological civilizations may rather rapidly transform themselves into pretty much whatever they want to be, at least with respect to that fraction of the civilization that takes off on this exponential and may leave much of the rest of the civilization behind, which also concerns me. But it's something that human civilization has made its peace with for centuries. I'm about to say have a nice evening, but all the way back, and I'll take one or two more and then we'll stop. Yes, sir.
You talked about intelligent life and surviving that transition. What would you say the likelihood of intelligence surviving intelligence is?
Well, that's the question, right? I have no idea what that probability is. We've gotten through 50 years of nuclear power. Not nuclear power, that's not what's important. We've gotten through 50 years of nuclear explosives. The dilemma is that nuclear explosives, in one sense, are easy compared to the dilemma posed by biotechnology. Because it's hard, it's getting easier, unfortunately, and that's the lesson of the AQ smuggling network. But it's hard to make the materials you need to make nuclear weapons, whether you're talking about uranium, high-enriched uranium, or plutonium. And that's what makes it possible for the International Atomic Energy Agency to monitor only about 1,000 facilities around the world and keep track of what people are doing. It's imperfect. It's clearly imperfect, but it's plausible. You can actually have a kind of global monitoring regime so that most of the time we know who's doing what where. Challenging, but You know, JFK in one of his press conferences in '63 said that by the mid-'70s there would be 15 or 20 or 25 nuclear powers in the world. Here we are in 2006 and there are about 8, maybe 9. The dilemma posed by biotechnology is that biological weapons resemble cyber terrorism much more than they resemble nuclear weapons. Right? Imagine if you were trying to have an inspection or monitoring regime for cyber terrorism, you'd have to keep an eye on the hundreds of millions of computers around the world that are hooked up to the internet. Obviously an impossible thing to do. And as biotechnology becomes easier and more black boxed and cheaper, it resembles more and more the cyber end of that spectrum than the nuclear end of that spectrum. There's no way we're going to have an inspection regime or a monitoring regime for biotechnology. At least not until after some total catastrophe when people charge the labs with burning torches. We're in a realm, I think, with respect to biotechnology, we're about to enter a realm where the kind of Cold War models of arms control and nuclear non-proliferation just don't apply. And nobody right now has a good idea for what kind of global system we put in place to deal with the challenges of biotechnology. Again, this sense that substantial power is going to be placed in the hands of small groups of the technically competent. People are scrambling to figure that out, but there aren't good answers yet. So to me, that's a cause for pessimism as far as it goes. I'm actually an optimist about the human future. We got through the Cold War, and you know, it's up to us, and in particular, it's up to the young people in this room, and it's up to the students at places like Princeton or any other university in the world to figure out how we're going to get through the next few decades, because it's going to require a lot of thinking that doesn't bear close resemblance, I think, to the thinking we had to do during the Cold War. One last question? Yes, sir.
Before you alluded to the two theories around impact that and you went into some detail on life being a product of the impacts, but you said that perhaps life could not develop until after the impacting period had ceased, in which case it would have developed pretty quickly thereafter. Would that then argue that the probability of the creation of life is relatively high if it occurred so quickly thereafter?
So I think probably most of you heard the question, which is a really insightful question that has been debated in the origin of life community over the past 10 or 15 years. The idea that to the extent we have evidence that life originated on Earth right after the end of the heavy bombardment, does that mean that the origin of life took place quickly? And does that in turn mean that somehow the probability of the origin of life might be high? Of course, we don't really know the answer to any parts of that chain of reasoning. But there was a time when people thought that they had pretty good evidence for life on Earth 3.8 billion years ago. As I said, that evidence is now quite questionable, but probably by 3.5. But pretty good evidence for life by 3.8, and the heavy bombardment falling off right at that time that people would say, looks like the origin of life took 100 million years or less. And that's a small fraction of the age of the Earth, so the argument would go, as you said, maybe that means the origin of life is quite probable. What I'd say now is that the dilemma is that the evidence that we have for the origin of life that's reasonably reliable is 3.5 billion years ago. We don't really know that the heavy bombardment was a complete impediment to the origin of life. Probably the only part of the heavy bombardment that was a complete showstopper were these big ocean evaporating events. And those arguments require working with the statistics of small numbers. The numbers turn out to be several, scattered over the first half a billion years of Earth history. And the probabilities, when you work the Poisson distribution, you work it out. The number could be 0, the number could be 6, it could be 3. So all you can really say is that you have hundreds of millions of years and maybe closer to 1 billion years to work with. And as soon as you're in that realm, then the length of time it takes for the origin of life is about the same as the age of the Earth, and therefore you really can't say anything. So it's too bad. there have been, just really animated discussions on this topic at a whole variety of conferences, and the answer at the end of the day is, well, gosh, that's interesting, isn't it?